What we're looking at here is chi-squared goodness of fit models or tests. And in this particular one, we're seeing if our data fits a probability model. And this is quite a common one. So what I've done is I set up a little question here where we've got casino dice that are being tested to see if they're biased. So we've got the observed data here. So it came out on a 1 12 times and on a 2 28 times, etc. Our null hypothesis, and you should be used to doing null hypotheses if you've been doing t-tests and independence hypothesis. Our null hypothesis is always that it will fit the required amount, so the not biased. So that means we would expect to get 20 here, and 20 here, and 20 here, and so on, because we're doing 120 rolls, and we're dividing it by 6 to get 20 in each category. So that's our null hypothesis. Our alternate hypothesis is that the dice is biased. We're also going to write down our level of significance, our alpha value, which is 5%. We get that straight away from the question. And then you'll be used to using degrees of freedom. Now for a goodness of fit, you look at how many categories. So I've got 6, you take away 1, so you have 5 degrees of freedom. We're going to need that later. So the next thing to do is to think about the observed data, which is in the green table there, and the expected data here. And although you probably won't have to do this too much, our chi-squared test statistic is gained by taking the observed, take away the expected. For each category, we're going to square it and we're going to divide it by how many we expect to be in there. So we're just going to keep doing that. So the second one is 28, take away 20. Now, I'm going to skip through doing this. I'd have to add all of these together and so on. I'm going to skip through and I'm going to find the answer to that using a graphic calculator. So if we grab our graphic calculator and we go into statistics, and what we do is we write out the frequencies in one list, then the expected frequencies in the other list. So I've got all those written out to save a bit of time. I'm going to go into test, and I'm going to go into chi, and this time I'm going to go GOF, goodness of fit. And it's saying my observed is in list 1, yes. Expected in list 2, yes. Degrees of freedom is 5. And we'll ignore this one for the time being. We'll just put all the answers in. And it gives me my chi-squared is 11.95. And my p is 0.35. So I'm just going to jot those down. My chi-squared is 11.95. And it also gave me a p-value, which was 0.035. Now, what does that mean? Well, as usual, we have to draw a diagram, or at least think about this diagram. It really helps. And I'm just going to think about the critical value. So this area in here is my 5%. My 11.95 is my test value, but I want to know what this critical value is here if I'm going to think about the critical values. So I'm going to go to my calculator and I'm just going to go back and I'm going to go to distribution chi, and you should be used to doing these now. 5%, sorry, inverse, then 5%, degrees of freedom are 5, and it will tell me that it's 11.07 is this cutoff point. So this is if I'm using the critical values. But my chi-squared value comes within this. If I go back to the previous one, it's 11.95. So from this, I'm going to conclude that the dice is biased because within here, we reject HO. Now that's using the chi-squared critical values. What you could do is you could take it one step further. We could do it with the p-value. This is the kind of more normal type of thing to do, is to do the p-value, make a nice chi-squared And let's say we're at my cutoff point here, and that's 5% because that was my level of significance. Now, if I go back and look at my p-value, we've got 0.035, so p is within here. That means I am again going to reject HO, similar to the last one. It all ties in very, very similar to the chi-squared of independence and even the t distribution.